So today we will discuss about the one more important aspect or the concept which is referred to as the current mirror circuit, right? So as you can see here right in front of your screen, first let us try to understand what exactly we mean by the current mirror circuit and why the current mirroring is required in your MOS amplifiers. Basically, when you look at this definition, the current mirror circuit, right, there will be some output current which will be a mirror of some reference current, right? So let me take this as, say, I out, the output current, okay, which will be the mirror image of some input current, right? Let me call this input current as some reference current, something like this, the reference current. Now, why do we need this? That is the question. So before that, we will first try to understand the basic definition of the current mirror circuit here. Later, we will go into the details why we need the current mirror circuit. Now, let me give you one circuit. Please note it down. I have, say, VDD here. Then I have got one resistance. I am basically using a resistor bias circuit here. You can take it something like this. Then I have one more resistance here. Then I will take my device here. Something like this. All of you please copy down this thing. So this is my source. So this is my drain. This is gate. There is some problem with the internet connection. And this is source. And this current I will mark as the output current I. Write it as I out. And this is my drain. Okay, so let it be okay. And this side I will write this as R1 and this as R2. This is VDD. Let me take the things like this. Now, when I have the things like this, this basically represents a basic current mirror circuit, and this current mirror circuit, the basic current mirror circuit, is referred to as the circuit in which the output current is forced to equal the input current. The circuit in which the output current is forced to equal the input current. Output current is forced to equal input current. This is what we mean by the current mirror circuit, right? Now, the next question is why the output current is to be forced to the input current. That is the next question, right? So this is where the basic the aspects of your MOS differential pair comes into picture, right? So now when I use, so this circuit here, whatever I have used here, okay, it is basically called as the resistor divider bias circuit. This is referred to as the resistor divider bias circuit. So what exactly is the meaning of resistor divider bias circuit? So now I have VDD here, as you can see, VDD, and I have got one MOS device whose output current, now suppose if you take this IDD or this MOS device, if it is not connected to this part, that is the resistor divider circuit, right? So your equation for the output current, we have already taken this equation, right? So what is that equation? ID, suppose if I take the current ID or the drain current or your output current would have been equal to half 1/2 mu n COX, we have already taken this equation, COX into W by L into VGS minus VT whole square. This is the equation which we have already taken earlier, right? Half mu n COX W by L VGS minus VT whole square, where mu n is the effective charge mobility carrier, COX is the oxide capacitance, W by L happens to be the ratio of width to length of the channel, VGS is the gate to source voltage, and VT is the threshold voltage. So this is what is the equation, right? So now this ID is nothing but I out for me. This ID is nothing but I out, the output current, right? So now whenever I have the output current in any kind of devices, so it should be constant regardless of the output resistance. The output current is required to be constant in any application, right? You always wish to have the constant output current regardless of resistance. I expect all of you to please note down these things, because there may be some problem in writing these things, right? So if you are able to copy these things while I am telling, nothing like that. So the output current will be always required to be constant regardless of the resistance. Then only you will be able to get the exact application of this MOS devices or the differential pair or the differential amplifier, right? But here what exactly happens in this particular case is, right, when you have ID is equals to half mu n COX W by L into VGS divided by VGS minus VTH whole square, right? So this particular expression, whatever I have written here, right, it indicates the dependency on three basic parameters, right? I will tell you what are those. The first one is the supply. It is dependent on the supply. The second one is it depends also on the process, and of course it is also dependent on the temperature. These three parameters are going to affect the value of ID or your I out because of the nature of the equation, right? Supply, you can understand, you have VGS and VT. Process, what do you mean by process? Process is how exactly this particular MOS device is being manufactured, right? So that particular aspect will include this mu n and COX oxide capacitance that depends on the different layers, or what we call it as the wafers, right? The basic wafers are used to produce this semiconductor devices, right? So depending upon the number of wafers or the nature of wafers, right? So your value of the oxide capacitance and mu n depends. Of course, this mu n also depends upon the value of the temperature. So that means whenever there is an external variation of these things, right? Maybe the supply or the very process due to which these MOS devices are manufactured, or if there is any variation in the temperature, then your I out is not going to be properly defined, but it is called as poorly defined. I out is poorly defined. Please note down these things. I out is said to be poorly defined. What do you mean by saying poorly defined? So the external parameters will affect the value of I out, and what it is supposed to be, it should remain constant regardless of the resistance, right? So it no longer remains constant. Your I out no longer remains constant, right? So that means if the VGS is properly defined for a MOS device, your ID need not be properly defined. So it has got the variation because of some external influencing factors, and when your ID is not properly defined, when it is poorly defined, now we have to make it somehow to get properly defined. So for which what we do is we will take the value of I out or ID as a function of some already defined reference current, some already defined or already standard reference current, and obtaining this kind of output current, right, from a reference current, right? Obtaining the output current from a reference current is said to be a current mirror circuit. Basically, it is based on the process of copying the current. The main idea here is to copy the current from some standard reference, right? So this process is referred to as the current mirroring, or such circuits are referred to as current mirror circuit. So now what we will write here is, it is I'll just write it here, copying the current from a known reference, copying the current from a known reference, assuming that one current source is well defined and is already available. So this process is called current mirroring, copying the current from a known reference, assuming that there may be some small spelling mistakes, right? Assuming that one current source is well defined and which is already available. Now the question is how to generate the copies, how to generate current mirrors. How to generate the current mirrors. We will try to see a circuit here, right? As usual, what I had written earlier. So I take VDD here, then I have I reference here. So it may be because of the voltage divider bias circuit or whatever we have, right? So we have I reference. Here I do have a copying circuit. Here I have a copying circuit, something like this. Then this output I give to the MOS device which I am interested in. So now here, this is going to my output current. I out. Please try to write it properly. There is some small problem in writing these things because of the network issue. Okay, so this is my VDD, this is my VDD, and this is my I reference. This is my I reference, and this is copying circuit. This is my transistor Q, and needless to mention that this is drain and this is source, because this is gate. So this is the copying circuit. Now we will try to see what exactly this copying circuit consists of and how we will be able to make this I out independent of the supply, process and temperature which is involved in the manufacturing of this MOS device as well as its operation. So now when I know that I have got a standard reference current here, right, and if I make the output current as a function of this reference current, then whatever the external parameters, could it be the supply, could it be the process, could it be the temperature, they are not going to influence the output current, and your output current becomes independent of all these things. So which is the necessity in operating the MOS based devices, right? So now we will try to see how exactly we are able to do this. So now for a MOSFET, you can write these things. For a MOSFET, now we know that we have already got the expression for the drain current. Of course, if you assume that these things are constant, your ID is directly proportional to VGS. Okay, so we can write it here. ID, the drain current, is definitely a function of VGS, f of VGS. I write it like this, f of VGS, right? So it is basically the relationship between ID and VGS. And now if I write VGS, definitely it will be an inverse function of ID. VGS will be an inverse function of ID. So this is a very important equation for us to arrive at the concept of current mirroring, right? So VGS is an inverse function of ID. Now let us say if a transistor is biased at I reference. So now this is what is the biasing current what we give for this transistor. And again, by looking at this circuit, you know that I reference is the biasing current for this transistor. If a transistor is biased at I reference, if the transistor is biased at I reference, then definitely it will produce VGS, which is an inverse function of I reference, right? It produces VGS as an inverse function of I reference. So now this I will show in the form of the diagram again, right? So I have VDD here, then I have my I reference here, then you can see the transistor being drawn here. And here let me tell you one more important concept. That's what we call it as diode connected transistor. I will tell you what exactly is the meaning of that. Now I have a current source here, which is I reference for me. This is my I reference. Let me say that this is the transistor, say M, and here I will have F inverse of I reference. Please look here. Of course, this is my VDD. Now, if you look at this diagram, okay, so this is my drain, this is the gate, and this is the source. Now, in this diagram, your drain and gate are connected to each other, which we have not seen earlier so far, right? The drain and gate are connected to each other, that is shorting the drain and gate, that is connecting or shorting, connecting drain and gate will lead to one special operation. I don't know whether you have studied these things in your analog electronics or not. This is called as the diode connected transistor. Diode connected transistor. So what you understand by a diode connected transistor is, see, this VGS, the voltage between gate to source, VGS, is, since gate is connected to drain, so it will be always equal to VDS. That means you are basically making your transistor to always operate in the saturation region. Saturation region. Because our all assumptions, when we have taken the expression for ID in the previous case here, when I have taken the expression for ID, so this is the current when the transistor is operating in the saturation region, right? So when I have connected the drain directly to the gate, the transistor is not operating either in the cutoff region or in the triode region, and the transistor is always operating in the saturation region. It will never operate in the the linear region, right? So that will make my expression for ID validated for whatever the analysis I am going to take here, right? So this is called as the diode connected transistor. Diode in the sense, this point D is directly connected to G, right? It is acting as a forward biased diode. Okay. So now with this we will proceed further. I have now, if a transistor is biased at I reference, it produces VGS, which is again of course equal to inverse function of I reference. Okay. Now if the voltage is applied, whatever the voltage that we are going to get here, let me call this as plus here, right? If this voltage is applied to gate and source of the second MOSFET, right? If I write it here, if the voltage is applied to the gate and source of the second MOSFET, gate and source of second MOSFET, let me draw that because we have started from that very diagram, right? If the voltage is applied to the gate and source of the second MOSFET, what happens here? You can see here the resulting current let me write it as I out, resulting current I out. So what will be the value of I out? Before that I will draw this diagram. You can see here, now this is my VDD, this is my reference current. Same diagram which I have just drawn, that I am repeating here. So from here I will connect it to one MOS device as it is, like this, and of course this is connected to the drain, and now here this is connected to ground. This is my I reference, this is VDD, so now let us say that this is having some value of W by L, because each transistor or each MOSFET is characterized by its own W by L ratio, right? So now up to here we have already drawn in our earlier diagram. Now what I am trying to do here is, if this voltage is applied to the gate and source of a second MOSFET, so now I have got a second MOSFET here, wherein this current I out I want to have independent of the supply, the process and temperature. So this is source again, right? So now this is M2, this is the transistor, say M1, you can use Q1, Q2 also, right? So now this is source, this is gate, and this is drain. You can see the gate of the first transistor or the first MOS device is being connected to the gate of second MOSFET. So now this diagram, whatever I have shown here, this represents the basic current mirror circuit. So now what will be the expression for the output current? It will be the function of, okay, inverse function of I reference. I hope you can understand what I have written here. Inverse function of I reference. So this becomes I reference only. I out becomes equal to I reference. So now if I want to show you all the things in a single window, you can see here we have ID, which is a function of VGS in one transistor, and of course that leads to show you that VGS is an inverse function of ID. Now if a transistor is biased at I reference, right, then it produces VGS, this VGS, which is an inverse function of I reference. So now this VGS or this voltage you are applying to one more transistor here, right? So obviously the output current I out will be a function of inverse function of I reference. So therefore you are going to have I out is equals to I reference, and this circuit, whatever we have drawn here, is referred to as basic current mirror circuit. This circuit is referred to as basic current mirror circuit. Now we have understood how exactly it is possible for us to have the output current to be dependent on some already known, the reference current, and from that reference current how it is possible to make the output current independent of the supply, process and temperature. So this circuit, whatever we have drawn here, is referred to as the basic current mirror circuit, this particular diagram. Okay, now you can see here two identical MOS devices having equal VGS. So now by looking at this diagram, we have got two MOS devices. One is M1 and another is M2. We have already written it here, of course, M1 and M2. If two identical MOS devices, that are having equal VGS, right, operate in saturation, then they carry equal current. Here one important parameter is that I have mentioned something about the channel length modulation effect in one of my earlier presentations. I will come back to this, right? We have neglected the effect of the channel length modulation, but before understanding what do we mean by neglecting the effect of channel length modulation, we should first know what exactly is the meaning of the channel length modulation. Of course, in my next presentation, I will take that the channel length modulation, right? So now, when we have neglected the channel length modulation of both of these transistors, then the M1 and M2 are said to be the current mirrors here. The M1 and M2, M1 and M2 are called as the current mirrors. M1 and M2 are called as the current mirrors. So this is a very basic, the operation or the basic concept behind having the current mirror, copying the current from one circuit to another circuit. In order to copy the current, what we need to have, we have to have a reference current source which is already known to us. Then we have to have one more transistor which has to operate in the saturation region. That is the reason why we have made it the diode operation here. The gate of the transistor M1 is connected to the drain of the same transistor, so that will always assure that the transistor operates in the saturation region. So once the transistor operates in the saturation region, the same voltage is now applied to that transistor whose output current has to be made independent of the supply, process and temperature. So therefore your I out will be equal to I reference, right? So now by neglecting the channel length modulation, by neglecting the channel length modulation, I will write it here, by neglecting channel length modulation, we can write I reference, the reference current, please refer to the previous diagram. I reference is equals to, say, 1 divided by 2 mu n COX. Now the first transistor, let me take this as W1 by L1 as long as the first transistor M1 is concerned, right? So this into VGS minus VT whole square. This is my equation number 1. Then the output current I out, the expression for I out is given by 1 by 2 mu n COX. So this will be W2 divided by L2 into VGS. We have assumed the same value of VTH. Of course, VGS will remain same by looking at the circuit for both the transistor M1 and M2. So this is my equation number 2 where I have the expression for I2, right? So now I have I out here. I have I out is equals to W by L of second transistor divided by W by L of first transistor into I reference. So as long as you know the W by L ratios of both the transistors, because any transistor which is manufactured, any MOS device which is manufactured, in its data sheet or in its catalog, you will be having the W by L ratios. So you can precisely understand what will be the value of I out with respect to I reference. It need not be same as I reference. It is the ratio of W by L which matters. In if you select the two similar transistors with W by L of 1 and W by L of 2 same, then your I out will be equal to I in, right? So now it allows the copying of the current without depending upon the process and temperature, and this is referred to as the current mirror circuit, right? So basically it is used in the manufacturing of the IC amplifiers, differential amplifiers, op amps and all. So any application would want the output current to be constant regardless of the external conditions as well as the load conditions. So if you want to keep the output current constant, and whenever you may have this circuit for biasing the transistors also, you will be biasing the transistor with a constant current source, right? So getting a constant current source which is ideal will be always difficult. The constant current source will be having the impedance which is very less, which is ideal it is 0. It will have its own effect on the loading of the transistor. So in such cases, what you can do is you can make use of the current mirror circuits which will always give the constant current irrespective of the loading conditions. In such cases also you can make use of the current mirror circuit. So basically a current mirror circuit is used in order to force the output current equal to the input current or the reference current, right? Generally it is used to provide the bias current, and it is having the features of low input resistance to keep the input current constant. I repeat, low input resistance, right? So we never have seen the cases of low input resistance. We have got very high input resistance or input impedance, so that the circuit draws a minimum current. But when you have the low input resistance, the input current will remain constant regardless of the condition, and high output resistance, right? The output current is constant regardless of the output conditions, regardless of the load condition. And basically a circuit that is designed to copy the current through one active device to control the current in the other active device, right? Keeping the output current constant regardless of the loading condition. So how exactly we arrive at the current mirror circuit we have seen, but here what exactly we have seen is we have made one important assumption where the channel length modulation factor is neglected. Otherwise this equation, whatever we have written here, equation number 1 and 2, they would no longer have been same equation had I considered the effect of channel length modulation, right? When I consider the channel length modulation, these equations will not remain as what you are seeing here. It would have been different. But when I consider the channel length modulation, how the current mirror circuits behave and what modifications are required to be made in the current mirror circuits, that we will take up in the cascode current mirror circuits, which is also of course a part of your curriculum, your syllabus if you have seen. In fact, it is the last part of that, the cascode current mirror circuit, right? So cascode current mirror circuit means connecting a common source stage with a common gate stage, that is CS, common source with common gate. I will tell you what exactly is this. This is not cascade, right? You know the literal meaning of cascade, but it is called as cascode. It is connecting the common source stage of MOS device with a common gate stage. By connecting so, in what way we will be able to overcome the effect of the channel length modulation, and what are the other advantages of connecting two transistors in the cascode stage, what other benefits we are going to get in the cascode stage, that probably we shall see in our next presentation. Okay, so now with this I will stop the presentation now.